Hello everyone. Welcome to this AtLAST forum. My name is Pamela Pizarro, and along Carlos Ibroic, Juan Pablo Perez, and Angelo Darola, we've been working during this year in the characterization of the wind conditions at two sites on the Chajnantor Plateau. So for any astronomical project, it is really important to understand the relevance and the impact of the atmosphere to making the right decision both for construction and also for future operation. So in previous work of this work package led by Carlos Ibroic, have already chosen two sites that have been explored. Now we are going to individualize it at site 1 and site 2. And what are most needed are the wind speed measurement that at least must be 4 times higher height above ground than ALMA. So that's why ALMA is around, and then from the AtLAST has installed dedicated weather towers in that place. So where are these sites located and where are these weather towers located? So we have site 1 that is within what is known as ALMA concession next to Apex. And also we have site 2 that is a little bit up north within what is called the Atacama Astronomical Park concession. And as we can see here, site 2 is surrounded by Cerro Toco and Cerro Chajnantor. So at first sight, we have some difference between both sites. Both sites are located in the Llanos de Chajnantor, and also it is important to remark here that since the local time is around UTC -3 and UTC -4, from now on in this presentation, when we refer to times in UTC time from 0 till 11, we are going to be thinking in night hours. And when we are talking about 12 to 23 UTC hours, we are going to be considering day phenomena. So what is the wind data that we have available at sites 1 and site 2? So in both sites, there are installed these weather towers that have sonic anemometers installed at different heights. In site 1, there is measurements available from levels 1.5 meters from the ground, 12 meters, and 24 meters. And at site 2, we have available wind data from 1.5 meters from the ground and at 24 meters. And as we can see here at the image, we can see the weather tower with the anemometers that are installed at different heights and the comparison with the expected antenna size. So these anemometers have different sample rates depending on the anemometer, but mainly they fluctuate between 10 to 20 hertz. So that's why there is so many data points that for this analysis, I'm going to use 1 hour average. And the period considered where we have data available runs from 2023 until today for the anemometers placed at 12 and 24 meter heights. And there is a special measurements periods during 2025 and from now 2026 for the anemometers that are located at 1.5 meters from the ground. So with this data, we can see here that these are the anemometers. This is site 2. We have the one near the surface and the other one on the top of the tower. And there is equivalent tower at site 1, which also has one in the middle at approximately 12 meters height. So additionally, we are going to consider wind data from Apex and also precipitable water data, because since the sites only have information from the wind, it is important for this task also consider how is the behavior of the precipitable water vapor in the site. The period considered is the same from 2023 till today. And since the sampling rate obtained from the ESO archive data is at 1 minute sampling rate, we are also using this 1 hour average for these comparisons. So what are the results then from the data we have from the anemometers at site 1? Well, as we can see, the distribution of this 1 hour average that we have for the wind, we can see that at both 12-meter and 24-meter heights, the distribution are quite similar. They both have one mode that are really relatively similar. They are just a pair of decimals of difference, but the mean is relatively different. I mean, the mean at 12-meter high is a little bit bigger than at 24-meter high. And this is explained because of this tail that we have here from 15 meters per second till 25 meters per second, that we have a higher density of the probability that contributes to obtain this bigger mean at this 12-meter height. But they are really similar, so we can expect that the wind at 12-meter high and 24-meter height at site 1 shouldn't be so much different. But there is a difference that we can see here clearly at 1.5 meters, and we can see a bimodal distribution of the wind. Of course, we have values of the wind speed that are lower than up to the up positions, but we have a clearly bimodal distribution that can evidence the presence of the diurnal cycle that is clearly marked. So we can see there, and we are going to go deeper on that later on this presentation. So since we have a lot of data from 2023 till today, we can get these heat maps where we can represent how the wind in the 1 hour average behaves during the time of the day, in UTC hours, and the month of the year. And we can see that wind is more intense during the afternoons. That is an expected daily cycle, and is also stronger during spring and also from winter to spring in the southern hemisphere. And that wind tends to increase with high. The differences are not so marked, but it can be noticed that in a little decimals, it also tends to increase in height. So the darker colors here can show you that there is more wind in this month of the years from June until November, and also in the days and the hours of the late afternoon. So what happens now at site 2? At site 2, we also have this bimodal distribution when it turns to the 1.5 meters height anemometer, but we also see that pattern at 24-meter height that we didn't see at the site 1. Here is clearly marked that there's 2 modes in both distributions, and there also it shows how the wind increases in height and for both modes and also for the means. And there is also the clearly marked how this distribution has 2 different modes that can be explained by the diurnal cycle. So also here we have just at 24-meter height a wide amount of data that enables us to build this heat map where we can see that the distribution for the 1 average for the hour of the day and the month of the year, we can see also in darker colors how the wind is more intense during the afternoon and during the winter and spring season, and follows the same trend as shown on this previous slide, in slide 1. And if we look at the values that we're going to compare soon, wind in general tends to be a little less intense than in site 1. So because of that, is that we made that plot. And now we can, we did the subtraction from both heat maps, and we can see clearly that when wind is here in the blue colors, wind is lower at site 2. We did the subtraction site 2 minus site 1. So it is clearly that for most of the time during the whole year and for almost all of the hours of the days, we have lower winds in site 2 than in site 1. I want to remark what happened here in February. For all you know, if you don't know, during this season that are the summer season in the southern hemisphere, usually happens the altiplanic monsoon. And what happens at the altiplanic monsoon is that there are changes in the humidity and also in the precipitations, and that also there are changes in the whole column in the atmosphere that affects also the change in the winds. So that is something that can be expected to happen during February. So even though we have these results here for February, we can say that for almost all the year, we have lower values for 1 hour average for the wind at site 2 than at site 1. That is consistent with previous results from this same work package that have been presented previous talks for Carlos and also Angel. So as a summary, we can see that in the main, the mean wind speed, if we take that distributions and put it together to make a comparison, we can see that site 1 usually shows higher values for the mean wind speed, higher values than in site 2 in terms of taking 1 hour average of these wind measurements. So if we remember previous slides before, we were discussing that there was this kind of bimodal distribution, especially near the surface when we were talking about the wind at 1.5 meters height. So we split the data and tried to look what was going on in these two regimes, night and day, splitting by the hours from 0 to 11 and 12 to 23 in UTC time. And as we can see, it is clearly marked the differences of the distribution that were seen before for site 2. And for site 1, we also see that at 1.5 meters high, but it's also noticeable at 24 meters high. Maybe it's a little more overlapped, but we can see what is expected, that stronger winds tends to occur during the afternoon or during the day and the afternoon, and that lower values of wind are expected to happen during the nighttime in both sides. So that's completely consistent with the normal behavior of the boundary layer. So when we summarize this, we can see then that at site 1, we have always larger values for the wind speed at both heights, 1.5 meters, and also 24 meters at both regimes, at night and during the day. Now, we could ask ourselves what's going on with it at 1 hour, because I mentioned that the sampling rate was between 10 to 20 hertz. So we have a lot of data points in 1 hour. That means that we could have also a lot of variability with it than 1 hour of data of the wind. So we need to think what is going on with it at 1 hour itself. So I took also the standard deviation and make this ratio between the standard deviation and the mean of that 1 hour for all the cases that we have. And what is interesting to result here is that even when we have lower values at site 2, what is interesting to see is that especially during the night, for both heights at 1.5 and 24 meters, what is interesting to see is that in site 2, there is more variability, or is more easy to find cases when we have more variability within that 1 hour. They're pretty similar if we see for the day cases at 24 meters or at 1.5. They're not that different, but they're especially different when we see what happened during the night and site 2. And that could be explained, is an open question, but it could be explained due to the terrain. If we remind the first slides, we saw that site 2 is surrounded by the Cerro Toco and Cerro Chajnantor. So the katabatic winds that may occur during the night could contribute to this special more variability in the night for the wind within that 1 hour when we were taking that measurements. So that being said, we also need to see what was going on nearby with the apex data, because it is important to consider also what happened with the precipitable water vapor and the wind both at the same time. Since we don't only have the data for the precipitable water vapor from apex, we're using these measurements to establish some thresholds. So the first threshold we set is consider the wind speed at 6 meters per second and the precipitable water vapor at 0.7 millimeters. And in that case, the darker color shows when it's better to operate under these conditions that are mentioned. So we have one plot on the left that shows when it's better for the wind using the threshold of 6 meters per second, and when it's better for the precipitable water vapor, considering this threshold in the right panel, also with darker colors. And if we combine these two conditions, we can get a final plot that summarizes what we have been saying here, that when both conditions are satisfied, so the wind speed is below 6 meters per second and the precipitable water vapor is below 0.7 millimeters, established by month of the year and hour of the day UTC, using the weather data from 2023 to 2025 in apex, we can see from the darker colors that these are the hours of the days and month of the years where better conditions are found to operate. And we can see that all that happens during nighttime and also from winter to spring season in the southern hemisphere. This means the higher values are around 35% of the measurements from this period from the apex data satisfy these conditions. And if we change the threshold now to wind speed at 12 meters per second and precipitable water vapor at 5 millimeters, we can also use these darker colors to find the better conditions for operation. And I want to remark this because in February here is shown that it's really dark and it could be a good time for doing observations. But for now, these are filled with a dark color, but they're nuns. In February, usually there are less observations for the precipitable water vapor, especially due to the altiplanic monsoon, because the shutter is closed in apex, so there are not data points for precipitable water vapor available during this time. So taking that into consideration and making this combination of plots to get now when are these measurements satisfying both conditions, that the wind speed must be below 12 meters per second and the precipitable water vapor must be below 5 millimeters, also by month of the year and hour of the day in UTC, the same period of data from APEX from 2023 to 2025, we can see what is also expected, that almost during the whole year, from April till December, especially during the night, is when the better conditions are found to operate, and it relates what happens now with APEX and what happens now with ALMA as well. So now we need to explore what is beyond that 24-meter height. If you see this image that I have shown before, we have the telescope that it's quite big, and we have measurement just up to 24 meters. So we need to fill this gap, and we need to know what might be going on there. So that's why we try to use a model to define what the vertical wind profiles are. So the most basic model we can use is the logarithmic wind profile. That has been taken under a specific consideration when the atmosphere is typically neutral, and in that case, we can relate and have this a relationship between the wind at the different heights as a function of the height with a logarithmic profile. And that will give us that the wind speed must increase with height, but only due to mechanical turbulence, and we are not considering other effects or thermal effects, etc. And for these calculations, we're going to use the ALMA memo results for the roughness length. And we also need to filter for the cases that satisfy this previous condition. So the wind, the simplified logarithmic wind profile can be applied. And also, we are going to use the data from October to November 2025 for site 1, and from December to January this year for site 2, because that's when we have information from 1.5 meters above the ground. So we have more information from the surface. So as we can see now, I have two examples, one for the day and one for the night, of what's going on in the vertical profile. And now if you can see, we can now put where data points with the information from that 1 hour average that we took. So we can see that the data points also follow the logarithmic profile for both night and day. And as we can see here, especially at the daytime, well, also here, but we can see that the profile is quite flat. That means that there are not so many changes within height. We can see here clearly that from 12 meters to 24 meters, there are not so many differences. And that's we have seen before in our distribution of the wind speed at site 1, that the wind at 12 meters and at 24 were really similar. So now we can see case by case, at every hour, we can see similar results, and that lead us to get a vertical profile that doesn't change that much in height. There is also this wide uncertainty that is due to the effect of the friction velocity, because friction velocity will affect the uncertainty, and friction velocity is calculated using the wind speed. So when we have higher values of wind speed, we are going to get more uncertainty. But in the end, if we see the slope of this vertical profile doesn't change that much in height. So the wind that we can see or expect at 30 meters height, it shouldn't be that different from the wind that we can expect at 60 meters. And the similar occurs for site 2. Here we only have 2 data points, and that's why it was really important to use this information near surface, because the only long-term wind data available we have was at 24 meters, and we need at least something that gives us information from the surface. So here happens something similar. The more the wind speed we have, of course, that increases our uncertainty, but it doesn't change that much the slope and also the gradient that we expect to see changing the wind speed with height. So we can project using these vertical profiles how the wind should behave at upper heights. So to get into conclusions, we can see from this presentation that the wind is systematically stronger during daytime, and that it happens at both sides, which is quite consistent with the boundary layer dynamics that says that with during the day we are going to hit the surface and getting stronger winds. During the afternoon, the wind speed is higher, and of course the calmer winds we are going to find usually during the nighttime. And also we saw other patterns related to the local climatology that APEX show us, and is consistent with also the data set from site 1 and 2. And it's important to mention that the wind distribution has 2 peaks due to strong difference in the wind behavior during the daytime and nighttime. And especially in site 2 are suggested to be related to the orographic effects for the presence of Cerro Toco and Cerro Chajnantor. And for the cases also previously described, we got these vertical profiles adjusted, and that led us to obtain an understanding of how the vertical behavior of the wind is. And it is important also for the turbulence that the anomalous refraction measurements simultaneously to the wind data is strongly needed. So that will allow us a better understanding of the local turbulence in both sites, especially what happens during the night in site 2. So thank you very much for your attention.